All right, hi guys. This is our second lecture for the kinetics chapter. And I was really stressed the last time I recorded, so hopefully we're all a little more laid back and hopefully you're all doing well. So I'm going to show you what Learning Suite looks like for you, just real quick. So this is what your view should look like, where you've got the electrochem quiz was due on Monday, homework 9 was due on Monday, classes were canceled on Tuesday, and then you can kind of see the lectures will be either here or here. This one will populate Thursday, March 19th. By the time you read this, it will say reaction mechanisms, and then it will say reaction mechanisms lecture on YouTube with a link. And then those will be the 2 lectures associated with this week. The quizzes associated with those lectures will close on Friday, March 20th, so you need to watch the lectures before March 20th. And then we'll have homework due on Monday, homework 10, sapling 10, and then also the quiz associated with the kinetics. Lectures for this week. So we're gonna switch to lecture now, and I'll just start on the slides. So I'm pretty sure we're here. So again, the Monday that's due on the Monday, the homework that's due on Monday is, oh gosh, is 7A problems 4, 10, 14, 15, and 16, 7B, 4, 6, 8, 16, 19, 20, and 22. And again, we're talking about mechanisms today, so elementary steps and then the rate determining step. We're gonna talk about those 2 things today. And then my office hours are going to be in over Zoom. So mine will be from 10 to 11, Monday, Tuesday, Wednesday, and then Jack and Kimberly and Esteban for my class will have office hours, and they'll get those set up. And then for Dr. Paxton's class, I think Ali and Taylor, I'm blanking on the name of the third one, they'll also set up their office hours. And then Dr. Paxton will be available for his class during Zoom. So we're basically kind of flipping the classroom where you guys can watch these lectures on your time, and then you can come into a virtual classroom and ask questions and kind of go over material. So my quote for the day is this idea that there is actually a lot of hope. We have hope from our prophet, we have hope from our leaders that these unique challenges will pass in time, and that President Nelson has said that I remain optimistic for the future. And I think that that is true. I think that we should do our best to make sure that we're sharing love and concern for others at this time instead of adding to the panic. So definitely practice good hygiene, stay home, don't arrange like game nights with friends, and just kind of do your best to kind of make it through. Okay, so let's talk about reaction mechanisms. So the rate laws, again, are telling us about the molecular level events that take place. And if you remember from the very first lecture of this chapter, we talked about how you can find your order in your reagent and how increased concentrations in your reagents A and B increase the rate, or if you just have molecule A going to molecule B, like what order that is. And so the order relates back to kind of a molecular level event. So how many molecules are combining together in space and in time to then produce the molecules that are formed. And so someone had previously asked in my class if the stoichiometric coefficients convert to the rate orders, like the orders of the reagent, and that is not true at all. In some cases it's true, but in most cases it's not. The stoichiometric molecularity has to do with kind of the overall reaction as opposed to molecular level events. So 2 examples of molecular level events are when you're thinking about a DNA double helix, what controls the rate of that formation from individual strands, or if we have ozone in our atmosphere and it converts to oxygen, what specific events are going to happen that you convert it into oxygen? So we're actually going to go through the example of ozone conversion. DNA double helix formation is way more complicated, but it follows the same fundamental principles, and chemists and biochemists have followed the fundamental principles to be able to determine what does control the rate of formation of a DNA double helix. We talk about ozone because it's much simpler. So when you have that chemical equation in front of you, we cannot convert that into a rate law. The reason why is that most reactions come from elementary reaction steps, where the elementary reaction is kind of a fundamental molecule to molecule reaction, and that's going to be many steps. So many elementary steps make up your final reaction. And so these elementary reactions describe a distinct and specific event, which is often a collision of the molecules or collision of the particles together in space. And so then what we have to do as scientists is propose a reaction mechanism, and the mechanism is going to be a sequence of elementary reaction steps. So you have kind of like 5 steps, and then the reaction mechanism says, step 2 actually happens first, and step 3 then happens, and then step 1. So you kind of arrange the sequence of elementary reactions into a reaction mechanism. So you would propose this reaction mechanism, and then you would test it with a series of spectroscopic experiments or increases in concentration to see if it matches up with the reaction mechanism that you've proposed. So this is a picture of molecules colliding. So these are 3 atoms, and this is 3 atoms, and these 2 3-atom molecules collide together to form 3 2-atom molecules. And so you can imagine that this would be ozone and this would be ozone. So O3 and O3, and those run into each other and they form 3 molecules of O2. So, so this is one option for the decomposition of ozone. So several different mechanisms are going to be proposed, and then rate measurements, so looking at concentration and rate, eliminate some of them. So this is an example where I'm taking 2 molecules of ozone and decomposing them into 3 molecules of oxygen. So that's the one-step mechanism, is you just take these 2 O3s and you collide them together and you get 3 oxygen molecules as seen here. So O3, O3 goes to O2, O2, O2. So this would be an example of an elementary reaction where I have the molecules are split up into individual components. So ozone plus ozone, there's no coefficients, and then they go into 3 different and specific oxygen molecules. So this would be an elementary reaction. Is that what we're calling it? Elementary reaction. Right here. So this would be an elementary reaction. This is not, because your molecules are not shown as specific entities in your reaction. So this would be the elemental reaction for a one-step mechanism. If you want to talk about a 2-step mechanism, you could think about ozone, O3, decomposing into O2 and an oxygen, and then that oxygen combining with an O3 to form 2 more molecules of O2. So we still have an overall 2 ozone molecules reacting to form 3 oxygen molecules, but those are happening in 2 different steps. So in the first step, we have O3 dissociating, and that means that we've broken one of the bonds to form 2 molecules from 1. In the second step, you have an oxygen attack. So that oxygen is attacking that ozone molecule and making 2 more oxygen molecules. So here's how you would write the elementary reaction associated with that first step. So here's our ozone dissociating, breaking up into oxygen and an oxygen kind of radical. And then step 2 is that ozone reacting with the oxygen radical from step 1 to form 2 more molecules of O2. And then again, if you wanted to see the overall reaction, you can just add up step 1 and step 2. So I can draw this here. So if we add these up, then this is our overall reaction of 2O3 goes to 3O2. So when you're proposing steps of a mechanism, you need to make sure that the overall mechanism still matches up with the with what you have. Okay. So this free oxygen atom that I'm calling a radical, we're just calling it an oxygen atom, is a reaction intermediate. Reaction intermediates are produced in one step, but then used up in a later step, and that species never appears in your chemical equation, your overall chemical equation. So remember that overall chemical equation that I wrote down here, where I have 2 ozone molecules going to 3 oxygen molecules. This intermediate cancels out. So intermediates are produced and consumed over the whole course of the mechanism, and so they don't show up in the chemical equation. And then the 2 equations have to add together to give the overall reaction. So I should have left that up, but I didn't know it was going to not run in. So let me draw that up again. So overall, this is where cursive comes in hand, right? Is 2O3 goes to 3O2, and this cancels with this. So oxygen intermediate You guys like my cursive? It's so good. So not in, so therefore not in overall. Okay. Okay, so this happens. Whoops. So this brings us to a new term called molecularity. So molecularity is a number of reactant molecules that are happening in your reaction. So in step 1, I have 1 molecule going to 2, and so this is a unimolecular reaction because it's only 1. So 1 thing going to 2 things, unimolecular. Step 2 is going to be biomolecular because we've got bimolecular, sorry. Ozone plus oxygen goes to then 2 things. So it doesn't actually matter what they become, it just matters what's happening on the left or reagent side of the arrow. So how many things are reacting on the left side, and that's your molecularity. So this is unimolecular, this is bimolecular, this is 1, this is 2. 1 is unimolecular, 2 is bimolecular. So on good practice, so let's talk about this a little bit. So when you're writing out elementary reaction steps, they're different than chemical equations because you don't write the state symbols. So I don't indicate that everything is a gas. I don't need to because I'm just saying this is the elementary reaction step. 2, you're only showing how individual atoms and molecules take part in the reaction, and so you're not writing any stoichiometric coefficients. So if you have 5 things coming together, you're going to write it 5 times. Even though it is faster to use stoichiometric coefficients, we don't use them when we're writing out elementary reactions. So elementary reactions are different than chemical reactions because in an elementary reaction, what we're communicating is how many molecules are reacting or how many molecules are decomposing over the course of a mechanistic reaction. So let's do this example. So practice A, I have ethyl bromide plus hydroxide, and that is forming ethanol and bromide anion. So I have, it went back. So I have these 2 molecules reacting together to form these 2 molecules. What is the molecularity? And then in this other example, I have bromine reacting to form an individual bromine atom and an individual bromine atom. So that's 1 thing going to 2. What is my molecularity? So the molecularity of the first reaction is that it's bimolecular, there's 2, the molecularity is 2. And the second one, it's a unimolecular reaction, and so the molecularity is 1. Okay, so to talk about the rate laws of elementary reactions, so to verify a mechanism, to verify that you have set up the correct sequence of elementary steps, you have to agree with the experimental data. And so you can perform experiments, you can calculate the rate law, and then this is how you would use your elementary reactions to verify your mechanism. So we have 2 options. We have the 1-step mechanism where we have 2 molecules of ozone coming together to form 3 molecules of oxygen, or we have the 2-step mechanism where you have 1 molecule of ozone decomposes or dissociates into the oxygen molecule plus an oxygen atom, and then another ozone molecule being attacked by the oxygen atom to form 2 oxygen molecules. And so we need to verify if it's this or if it's this. So proving a mechanism isn't like a math proof because we basically just pull together evidence to convince or give a consistent picture. A mechanism is not necessarily ever proved and is open to change based on more evidence being assembled. And so lots of mechanisms have changed over the years based on better instrumentation, upon better being able to kind of collect information about the system with instruments or better modeling. And so again, we're going to be collecting evidence to kind of give a convincing and consistent picture. But we may be still incorrect because maybe two mechanisms lead to the same rate law and you can't really distinguish between both of them. So that can sometimes be very, very hard. And so kinetic information, which is information about how rates change with concentrations, only supports a mechanism and never proves it. So, so this is how you would proof a mechanism from elementary reactions. So you're going to reconstruct the overall rate law by writing the law of each of the elementary reactions. So we're going to write out all of the elementary reactions and then combine them into an overall rate law. And there's two ways that we can do this. I'm going to tell you about the steady state approximation and then the pre-equilibrium way to do it. So these are the rate laws of your elementary reactions, right? So if I have A going to products, that's a molecularity of 1. The rate is going to be equal to the rate constant times the concentration of A. If I have a bimolecular reaction, I can either have reagent A reacting with reagent B to form products, or reagent A reacting with reagent A to form products. And so these give you kind of a different rate law. So you either have the rate constant times the concentration of A and the concentration of B, or the rate constant times A squared, right? And both of these would be second order rate laws associated with that elementary reaction step. If I have a termolecular reaction, I can have A, B, and C reacting. I can have A, and B reacting. I can have A, and A reacting. I also can have A reacting with B and B, or etc. So there's lots of ways for this to happen, but these are kind of your main cases, 3 of the same, 3 and 1 that are different, or all 3 are different. And so your rate is the rate constant times ABC if there's 3 things reacting, your rate constant A squared times B if it's only 2 things reacting, or your rate constant times A cubed reacting. And so these would be your rate laws associated with the elementary reaction steps. So again, these exponents up here are related to the number of reactants in the elementary reaction. So before, when we talked about the rate coming from experimental data, that rate law was experimentally derived. And now when you're using the elementary reaction rate laws for independent elementary reactions, now the exponents do relate to the number of reactants. So someone asked me about this earlier in class, and it's just you have to keep your 2 systems straight. So exponents are related to the number of reactants in an elementary reaction. So if you're drawing out something that has to do with a mechanism, then your orders directly relate back to how many of the molecules you have reacting. Whoops. Okay, so unimolecular means that 1 component is necessary to make the reaction go. Bimolecular means 2, termolecular means 3, etc. And so let's talk about an example of a proof. So this overall rate law has been determined experimentally. 2 molecules of NO plus 1 molecule of oxygen go to 2 molecules of NO2. The rate of formation of NO2, so this is the rate that has been experimentally determined, is a rate constant times NO2 squared times oxygen. So again, this is based on this chemical reaction, and these numbers don't necessarily have anything to do with these numbers. They happen to match up, but that's not because this is an elementary reaction. It's just because this is the experimental rate law associated with this chemical equation. So here's a proposed mechanism. The proposed mechanism is that 1 molecule of NO and another molecule of NO come together to form N2O2. That N2O2 then breaks up into 1 molecule of NO and 1 molecule of NO. So this is a rate of formation of N2O2, and then this is actually just the reverse of this reaction. So if we wrote this with equilibrium arrows, then that would be the rate of formation, rate of consumption, right? And so the forward rate of formation is going to be the rate constant 1 times NO squared, right, because I have 2 of those. And then the rate of consumption of N2O2 is K to the negative 1, just indicating that it's the reverse of the first reaction times the concentration of N2O2. So that's the first kind of step. And then the second step, okay, sorry, so this is where we say it. So step 1 is a fast bimolecular dimerization. So a dimerization is where I take 2 things and I make 1 thing, and then I take the 1 thing and break it up into 2 things. So this negative 1 is just the reverse. So the reverse is just a reference for later on. So then step 2 is I take oxygen plus this N2O2 dimer that I've formed and then break that up into NO2 and NO2. So the rate of consumption for this one of N2O2 is going to be K2 N2O2 times O2, right? So that's this, so the rate of this is rate K2 times A and B are N2O2 and O2. So this is a bimolecular reaction where I have oxygen colliding with that N2O2 dimer, and the reverse of step 2 is too slow to include. So usually when you're writing out experimental mechanisms and elementary rate laws, the elementary reactions of a mechanism is that you're usually going to have a fast step and a slow step. The slow step we're only going to write the forward of. The fast steps you can also go in the reverse of. So if something is fast, if an elementary reaction is fast, then that means that it has enough energy to go forward and enough energy to go back. But if an elementary reaction step is slow, that usually means it only has enough energy to go one way and it's not going to have enough energy to go in the reverse. So fast steps go forward and reverse, and slow steps only go in one direction. So we're going to combine steps 1 and step 2 to get our rate of formation for our mechanistic proof. And so this is the steady state equilibrium approach. So again, I've got these 2 NO molecules dimerizing. This is the reverse of that because it's a fast step. This is my second step, which is slow, right? So this is just the forward of that. So, so here's step 2. So if this is the slow step, the rate of your reaction is going to be only as fast as your slowest step. And so your slow step is always the rate of your reaction. So whatever mechanism you propose, whatever your slow step is, that's your step that matters for your reaction. And so we're going to take this to be our rate. So the rate of the reaction is going to be limited by our slowest step. But NO2 is a product. And so we're going to say the rate of formation of NO2 is equal to 2 times the rate of K2 N2O2O2. So this 2 comes from the fact that I've got 2 NO2s that are formed for each of the N2O2s that break up. So this is our rate of formation of NO2. So this rate is the rate for our chemical reaction because this is our slowest step. This 2 is in there because this is the rate, but we have 2 of those that are formed. So, so finally, these is just review. So if this is our rate of formation of NO2, we can't report it because you can only report rates in terms of things that can be experimentally measured. And N2O2 is an intermediate. An intermediate cannot be experimentally measured. What can be measured is things that go in and things that come out, right? So my O2 is what I'm putting in, and my NO is what I'm putting in from my overall chemical reaction. So my rate needs to be expressed in terms of the reagents, because any sort of law that I'm going to experimentally determine is going to be based on changing the concentrations in those reagents. And so if my mechanism includes things that cannot be measured, then it's not actually going to be provable. So I need to put my rate of formation, my rate of my reaction that I'm using in my mechanistic proof in terms of reagents. So all the intermediates have to be substituted out. And so what's nice is that you can actually express your N2O2 in terms of everything that it's consumed and formed in the reaction. So I'm going to take all of my steps that have formed N2O2 and all of my steps that react away N2O2, and I'm going to set those equal to the formation of N2O2. So we're going to start with step 1, combine all formation and consumption steps. So the formation of N2O2 is K1NO2, and then I consume it in the reverse reaction, so this is going to be so I form N2O2 by being K1 NO2 squared. I subtract it when I react for K negative 1 N2O2, and then I subtract it again for K2 N2O2. So again, the formation of N2O2 is going to be it being formed in the first step, and then it being consumed in the second step, and it being consumed in that step 2. So this is the reverse of step 1. This is the forward of step 2. And so these two consume, this one forms. Here's my arrows that show where these things are coming from. And so the formation of N2O2 is equal to its formation and consumption, right? And so some of these are going to be faster than each other just based on the rate constant, but that's fine. All we're worrying about is the algebra. We're not actually trying to figure out what's going on. So the algebra says that we're forming, we're consuming, we're consuming. So that's what you're going to do with all your intermediates. So if your rate determining step, your slowest step that's associated with your reaction includes an intermediate, then what you're going to do is find all the steps that form the intermediate and all the steps that consume the intermediate and equal them to each other. And then you can solve for that intermediate. So here's our formation of N2O2. Here's the formation of it, and then these are both consuming steps. And I'm actually going to set that equal to 0. So this is what's known as the formal steady state approximation. At steady state, all of the intermediates should remain at very low concentration and unchanging concentration. And so because they're at low unchanging concentration, we can set the formation of N2O2 equal to 0. We're going to say that formation is again unchanging. So the rate of that is small and unchanging, therefore it's equal to 0. And then you can take this step and rearrange for N2O2. So I'm going to take N2O2 out of these two terms. So I'm going to take negative K minus 1 minus K2 oxygen and multiply that by N2O2. And then I can put this on the other side of the reaction, multiply by a negative charge, and end up with N2O2 is equal to the rate constant of the step 1 reaction times NO2 squared divided by the rate constant of the reverse reaction plus the rate constant of the second step, which is this step here, times the oxygen concentration. So with this in hand and this being our rate, now all that's left to do is take this and this expression here. So let me circle it for you. So we're going to take this expression and we're going to substitute it in here for N2O2. This will now express the rate of formation, basically. So our rate, oops. So the rate of our reaction is determined by that slow step. And there was a 2 in front of it, right? So rate of NO2 formation. So rate of formed NO2 is 2K2 N2O2 times O2. So I'm going to take this and I'm going to sub it in for the N2O2. Okay, so if I do that, it looks really complicated and it doesn't look like our initial rate expression. So if you remember what our initial rate expression was, oh, I can't get my, whoops. Our initial rate expression was that the rate, the experimental rate law, was equal to a rate constant K times NO squared times O2. So it was a third order rate law, and it was second order in NO and first order in O2. So some of you might be thinking, this looks totally different than this. But what you remember is that we have the 2 steps. So we have step 1, was fast, and step 2 was slow. And so as a result, K1 and K -1 are going to be much, much smaller than K2 because K2 is very slow. And so therefore, okay, wait, I think I have this wrong. Let me erase this. This is not true. So step 1 is fast, step 2 is slow. Sorry guys, so step 1 is fast, step 2 is slow. That part was true. Step 1 is fast, step 2 is slow. I was just remembering to last lecture where I was talking to you about rate constants. And if you remember, the rate constant that was smaller had like a super long delay and concentration decrease. You remember that? And so K2 is much smaller than K1, right? So if you remember, reactions that go slow are reactions that have a much smaller rate constant. So this is going to help us here. So K2 is much smaller than K1 because step 1 is fast, step 2 is slow, and therefore this term right here is going to be taken to be 0 because this is much larger. And if that's taken to be 0, then what we have is by limits that term goes away and you end up with 2K1, K2 divided by K -1 is NO2, 2 over O2. And so now what we're going to do is we're just going to group this into a new rate constant value. So this is equal to Kr of our reaction, which is this, Kr. And then that ends up being our rate. So here's our K NO2 squared over O2 rate expression. So it does agree and it's the third order rate law. Okay, so the tricky part here, again, is this part that I got almost confused about, which is that you really have to think about which one of these is going to be fast or slow when you're arguing your rate law to be working. So again, slow rates are associated with very small rate constants, and fast reactions are associated with large rate constants. Okay, so this is the other way to do these reactions, and this is by the pre-equilibrium method. And so the steady state approximation method and the pre-equilibrium method are two ways to kind of verify a rate law. So a steady state approximation means that your intermediate is being formed and consumed at about the same rate and then it stays low. A pre-equilibrium means that your forward and your reverse reactions of a first step kind of reach a pre-equilibrium before they go on to step 2. So there's different ways to get experimental evidence for a pre-equilibrium. Pre-equilibrium is a really nice proof, as you're going to see. It's much shorter, but it's not something you can always say. You can't just be like, oh, equilibrium was established previous to step 2, because sometimes it's not, and then you can't make that assumption. But a pre-equilibrium, if you were to kind of see a concentration between the two before it moved on, then that's something that you could do. Okay, so this is our experimental rate law here. It's the same as last time. So, so we've got this. So here's our experimentally derived rate law. Here's step 1, and this is fast. Here is step 2, and it's slow. And so this is our rate of formation, rate of consumption, and then rate of consumption, right? So again, this is what we're going to base our rate law off of. And again, we've got to get rid of this intermediate. So what you can do is you can substitute in that expression. So let me, oops, I have to clear my drawings here. Okay. So what we're going to do is the target reaction is the same. The initial setup is a little bit different. So we're going to write the forward and reverse in one step. We're going to say that the rate of formation of N2O2, so the rate of formation of N2O2, K1NO2 squared, is equal to the reverse reaction. And so that's what you're stating in pre-equilibrium is the forward and reverse steps are the same. If the forward and reverse steps aren't the same, then you'd have to go to steady state approximation. So here you're saying that you have pre-equilibrium, and therefore you can just solve this problem for N2O2, right? So if I just take that, sorry, sometimes it's really hard to get the pen down. So, so we're just going to take this, divide by k negative 1, divide by k negative 1. That cancels. N2O2 equals this. And so if this is our rate determining step, this is our slow step, step 2, slow. So RDS is rate determining step. So if this is our rate determining step, then that means that I can now just take this and plug it in for N2O2. And what that leaves me with is, that I can then just take N2O2 is equal to this, and then I can plug that in to my equation. So again, that's from the previous slide. Oh, I don't know that I pushed record. Hold on, I'm all of a sudden really worried that I haven't been recording this whole time. Okay. No, I am recording. Sorry. Okay, sorry. I was really concerned. Really not good at this because I have not ever really done this before. Okay, so we're here. So we're substituting that back in, and that gives us our rate is equal to this, and so this all equals K, and then that's our third order rate law where we have second order in NO and first order in NO2. Okay. So we've been talking a lot about this rate determining step, and so in any example where you have a slow step, that is your rate determining step, and that's the step that's your slowest step. So when you think about potential energy and you think about things moving through potential energies, something that's fast, so I can have orange and blue molecules that are interchanging, they can go through that energy pretty fast and interchange that energy. The barrier to interconversion is low, and that's going to make a step very fast. If I've got just a little bit of energy I need to overcome to be able to convert into one and the other, that's going to be a fast step. If I have a lot of energy that's required to go from one molecule to another, that's going to be a very slow step, and that's going to be my rate determining step. So any steps that come after this very, very slow energy intensive step are not going to be included in the mechanism. So you just kind of rule them out as needed. So this did not animate in well. So so here's an example. If the following rate law has been determined for the decomposition of ozone, where rate of decomposition of ozone is equal to KO3 squared over O2. Here's my mechanisms. So step 1, step 2, this is my fast step, this is a slow step. And so my slow step, this is a forward step. Oh, so this is the slow step, so the reverse is going to be ignored. So the rate of decomposition of O2, so basically my rate is going to be K times O3. So if this is my slow step, then my rate is going to be equal to O3 oxygen and then a K value, right? So again, this is an intermediate, so we got to get it out. And so I'm going to take my forward is going to be decomposition of O2 is oxygen is K1 times O3. That's just this. So I think this is a typo. So rate of decomposition of oxygen, rate of formation of O3 is going to be K -1 times this reaction. So this is the forward, this is the reverse, that fast reaction. And then my final step is going to be the rate of consumption. So this is my slowest step. And so now I have to get rid of, my oxygen in there. So the rate of decomposition of O3 is going to be the formation, the consumption. Yep, so my rate of decomposition of O3 to line up with my experimental rate law is basically the rate constant of the forward reaction, so that's consuming my ozone, minus the reverse, which produces my ozone, plus my second step, so K2O3O, right? And so now I'm going to take this as my steady state approximation. I'm going to set it equal to 0, and I'm going to solve for this intermediate oxygen atom. So solving for that intermediate oxygen atom, I'm going to set it to 0. And then solve for oxygen atom. So then this all comes in together. And so then this is going to substitute into that oxygen atom expression. So substitute back into the rate decomposition of here. So, so here's my ozone, K13, minus, here's my K -1 oxygen, and then K1 oxygen. So this is my oxygen atom, and then this is my oxygen atom here. So I'm actually putting everything in terms of the oxygen atom just by getting rid of it here. So then I'm going to take all of that, combine that together, give my denominators, add everything on top, and I end up with 2 K1 K2 ozone squared divided by K -1 oxygen plus K2 ozone. So this is my rate of decomposition here. So K1 K2 O3 squared, K -1 O2 K2 O3. So my rate law, depending on what my rate law is, my slow step is 2, and therefore that would cancel, and I'd end up with oxygen, ozone squared over oxygen, based on that being the slow step. So this K2O3O is very slow, therefore we're going to take that to be 0, and then that gives us this, which decomposes. So here's what we learn about steady state approximation in the second example, which I went through really fast, is that in the second example where you have ozone decomposition, steady state approximation always requires you to make an assumption at the end about your rate constants of the reaction, and usually that your first fast step, the first fast step, has a higher rate constant than your second one, where you then can kind of cancel that out. So here's your alternate proof. Again, this is our target expression where we have it second order in ozone, inverse order in oxygen. So this is the rate determining step, K2O3 oxygen. And so this is the step we set equal to each other, K1 oxygen, K-1, K1 ozone is equal to K -1 oxygen times the oxygen atom. So I'm going to solve this for oxygen atom, which is going to give me oxygen atom equals K1O3 divided by K -1 O2, and I'm going to substitute that in for here. And when you do that, you end up with ozone squared, and then K1 times K2, and then K -1 on the bottom. And so then you're basically done. Pre-equilibrium is so fast. Okay. We're gonna do one last reaction. This is a very long lecture. Is everyone with me? Okay, so here's our proposed two-step mechanism. So we have H2A plus B, and that goes to BH plus HA minus. What does this look like? This looks like a acid-base reaction. So I have an acid, diprotic acid, and a base, and I form the conjugate acid of the base, and I form the conjugate base of the acid. And the reverse, which is very fast, so this is the first reaction, forward and reverse is very fast, followed by the conjugate acid, the conjugate base plus the base again, gives you another conjugate acid of your base plus the now fully deprotonated conjugate base of your acid, which is slow. So find the rate law with HA minus treated as the intermediate and write the equation for the overall reaction. Okay, so we're basically determining the mechanism for a diprotic acid deprotonation. So here's what we know. We're going to write down the first step, and we're going to write down the first step and the reverse of the first step as the disappearance of base and the appearance of base. So the forward is going to be removing my base by protonating it, and the reverse is going to be the appearance of base by the conjugate base of the acid deprotonating the conjugate acid of the base. And so that's going to be K1 times our reagents H2A times B, and the reverse reaction is K minus 1 times the protonated base and then the deprotonated acid concentrations. So our slow step is this second step where I have HA minus plus B goes to BH plus plus A2 minus. So this is our slow step, which is K2 HA minus times B concentration. So we have to get rid of this HA minus in order to determine our rate. So for the net disappearance of B, we have K1 H2AB, which is our disappearance of B, and then minus K minus 1 BH plus times HA, that's our appearance of B, and then plus our K2 HAB, which is our disappearance of B. So here's our disappearance of B, here's our appearance of B, plus minus plus. So now what I'm going to do is I'm going to solve for B using the steady state approximation. And so I'm going to have K negative 1 BH plus HA minus on this side. So I'm going to have K negative 1 times BH plus HA minus, and then I'm going to divide that by K1 times H2A plus K2 times HA minus, which is right there. So here's my K1. Did I do that right? Oh, no, I did it wrong. I was solving for the wrong thing. Sorry. Here, look, we'll actually solve for you before we go on. Turn the page and I was like, I did the wrong thing. So I was trying to solve for B. You want to solve for HA minus. Sorry. So we're going to do K1 minus H2A. B is not the intermediate B I can measure. Equals negative K minus 1 B H plus plus K2 B. And that is factoring out HA minus. There it is, HA minus. So now I'm going to divide both sides by this guy. So HA minus is going to be negative K1 H2A times B divided by negative K1 times BH plus K2 B, and if I multiply everything by a negative, then this ends up being subtracted by each other. Okay, so that's what we should see. Yes, so here's my BH plus, here's my B, here's H2A, B, and then these are added, but I think they should be, oh no, because this is a minus and then these are minuses, so they end up. Okay, so I'm going to sub that back in to B of this expression. So what they're doing here is they are subbing that back into B here. But I wonder, let me check something real quick. B equals K2 HA minus times B. Is that right? Let me check. B times B. Okay, So we've solved for HA minus, and I think you can just take that and put it into here, but they don't do that. What they do is they take this and they put it back here and here. So we're going to sub that back in into there, and we are going to get everything with the same denominators, and then we're going to simplify the expression by adding everything together and combining. And so then that gives us K2 times B times, what did this end up with? HA, hold on, I just think they're making this more complicated than they need to. So here's HA minus equals K1 H2A B over K minus 1 B H plus K 2 B. Okay, so when they go through all the rest of their math, which we'll look at real quick. So they find HA minus, we substitute it back into wherever we see HA minus in the steady state approximation. We get the same denominators, we simplify, first and third terms cancel, and so we end up with K2, K1, B squared H2A over K minus 1, BH plus K2B. So if you would have just solved for HA and plugged that in, you end up with K2, K1, H2A, B squared over K minus 1 BH plus K2B. So I don't know why they're plugging it back in to the steady state approximation. Once you use the steady state approximation to find your HA minus, just plug that back into your second rate determining step for the HA minus, which is your intermediate, and then you're done, because this is confusing, unnecessary math. So we're just going to plug that back in. This gives us our large rate constant. We know that that second step is the slow step, so this K2 term is going to go away. And so then we end up with K1, K2, B squared, H2A, K minus 1, BH plus. So this ends up being our rate for acids, for the acid reaction, if that makes sense. So again, I don't think you need to do the unnecessary math. You can just go forward. So we've got second order concentration in base, first order rate, so second order rate influence of base, first order rate influence of the fully deprotonated acid, and then inverse order in the conjugate base concentration. Oh, we made it, guys. This is the quiz at the end. So again, this is some really unnecessary math. So given the following proposed mechanism, predict the rate law for the overall reaction. So here's my slow step, here's my fast step, this is my overall reaction. What is the rate of the overall reaction? So is it A, rate constant times concentration of NO2 times concentration of chlorine? Rate is K, rate constant times the NO2 concentration squared times the chlorine concentration. Rate is the rate constant times NO2 concentration and the chlorine concentration. Rate is K, rate constant times NO2 Cl concentration times Cl. So the answer here is, I mean, you should pause it. The answer here is that the slow step is the one that matters most. And the slow step is your rate constant K multiplied by the concentration of NO2 and the concentration of Cl2, which is going to be A. A is your answer. Okay. So I'm going to stop. I'm going to put those slides on the next one and just stop with that. So, so what we learned today is that there's two ways to proof the mechanism of a reaction, and that's through the steady state approximation or the pre-equilibrium method. So steady state approximation method is that you're going to find your intermediate, you're going to set all of the consuming and formation steps equal to 0, solve for that intermediate, and then sub that intermediate back into your rate determining step. You could also sub it back into your long expression, but that requires, you're going to probably mess up with the math. The second thing that you can do is that you can sub, so you can assume a pre-equilibrium between A and B, set those two things equal to each other, solve for the intermediate, and plug that into your rate determining step. And so that gives you kind of your rate expression. So what you want at the end of the day is a mathematically derived rate expression based on elementary steps set up in a sequence, where your slow step is the one that's the rate determining step, and that mathematical algebraic derived rate law needs to equal the experimental rate law that was determined using concentrations and how they affected rates. And if those two things matter, then you have good evidence that you have found the mechanism, but it may not be the end all of the mechanism because they may be the same. So we'll pick up next time by talking about a little bit about rates and equilibrium constants. So we come back to that a little bit, and then we'll talk about effective temperature on rates. So, so again, don't get lost in the math. You should be fine kind of going forward. But again, if you have any questions, you guys can come in and ask those questions in those Zoom meetings. We can do more derivations from there. So anyway, thanks. I will see you again soon.